Okay, so you may be wondering, when are we ever going to get away from direct substitution? It seems like we just seem to be evaluating most of our limits with direct substitution. Well, it is finally time to move on to the more complicated limits, the more challenging ones. And one of our most powerful tools for approaching these more difficult limits rigorously is this theorem. It's theorem 2.7 in the textbook. So it basically says, if you have two functions that are equal to one another for all x values at least near the c, which is the number you are approaching, okay, where you want to calculate the limit, except possibly at c itself, which is the key part of this, right? It's like these two functions, we're saying they agree with each other everywhere except for at c itself. And if one of them, if the limit of g of x exists, or g, but whichever one of them exists, then their limits as x approaches c are actually going to be equal. Recall, we've seen this at play before, because when we looked at the function x cubed minus 1 over x minus 1, we saw that that was equal to x squared plus x plus 1. And so we actually used that to help us figure out, we had like a 1 and a 3, something like that. We realized that they were equal to each other in every way except that one of them was defined for x equals 1, this one, and the other one is not defined for x equals 1. And we used that to figure out the limit, because we said, well, let's take the limit as x approaches 1. In this case, it's undefined, but in this case, it's a polynomial, continuous, so we can do direct substitution. We got 3. So we actually were applying that theorem back when we looked at that example. I just didn't, cite it because we hadn't learned it yet. So the gist of this is going to be, if we have some kind of function which looks complicated and for which the it's not continuous at our x value, at our chosen x value. So in this case, x is approaching 3. And here we'll have 3 squared minus 9, which is 0 in the denominator. It's not in the domain, so it's not continuous there. We can't just do direct substitution, right? In fact, it's, that would be undefined. That doesn't necessarily mean the limit doesn't exist. It just means that we might need to do some algebraic manipulation to this, this function to simplify it to an equivalent function which is the same in every way except that it might be defined at 3. And in this case, we can do that like we did with the that example from before. We can do that by factoring. So the numerator factors here as x minus 3 times x minus 2, and the denominator, being a difference of squares, factors as x minus 3 times x plus 3. And we see the common factor, which can cancel, right? Reducing this to a limit as x approaches 3 of x minus 2 over x plus 3. All right. So that expression and the original expression are equivalent in every way except that this one is actually defined at 3, right? So they agree with each other at all x values except possibly c itself, the 3 value. Which means we apply that theorem and say the limits are equal. Okay, that's what we've done here. We've written that the limits are going to be equal. And now we can evaluate this limit. And since that's a rational function and 3 is in its domain, we can apply direct substitution. So that's 3 minus 2 over 3 plus 3, and we get 1/6. So we evaluated that limit and got 1/6. I'm going to stop recording now, and then in the next video I'll do a few more examples to highlight a bunch of different kinds of algebraic manipulation you can do to help you solve limits.